All right, let's dive into the most incredible, most efficient economy you can possibly imagine. And guess what? It's running inside every single one of your cells right now. We're talking about metabolism, your body's very own energy economy.
So take a look at this. At first glance, it might look like, I don't know, a ridiculously complicated city map. And in a way, it is. But this isn't London or Tokyo. This is the blueprint for a microscopic city that's bustling inside every single one of your cells. It's a factory, a bank, a whole logistics network, all rolled into one. And its entire economy? It runs on a single powerful currency: energy.
Any economy at its heart has two main jobs: making money and spending money. It's the same in the cell. The making money part, that's called catabolism. This is where you break down big, complex molecules, think about the food you just ate, to release a ton of energy. And the spending department, well, that's anabolism. It takes all that energy and uses it to build up the really important stuff your body needs, like new proteins or DNA. So, what even is this energy currency we keep talking about? Well, when you boil it all down, energy is just the capacity to do work. That's it, the ability to make something happen. It is the universal currency that pays for literally everything, from a star going supernova all the way down to one of your muscles twitching. Okay, so this energy currency comes in two main flavors. First, you've got potential energy. This is stored energy. Think of it like money in the bank, or the power sitting inside a battery. It's all there, just waiting. A great example is the energy packed into the chemical bonds of a food molecule. Then you have kinetic energy. This is energy in action, the energy of motion. It's the money being spent, the battery being used. And the cell, it's a master at constantly converting that potential energy into kinetic energy and back again.
But here's the thing. This amazing cellular economy doesn't get to just make up its own rules. Nope. It has to play by the rules of the entire universe. And there are two big ones. Two unbreakable laws of physics it has to obey. The laws of thermodynamics. Rule number one, the first law, is pretty straightforward. It's basically the law of conservation. You can't create energy out of nothing, and you can't just make it vanish. It's always there. All you can do is change its form, like converting the potential energy in your lunch into the kinetic energy you use to walk around. The total amount of energy in the universe, it's constant. It's a zero-sum game. Okay, now the second law. This is where things get really interesting and, frankly, a bit of a challenge for life itself. This law says that the universe is always, always moving towards more disorder, more chaos. Scientists call this entropy. Think about it. Your clean room naturally gets messy, right? It never spontaneously cleans itself. So that brings up a huge question. How in the world can a living cell, which is this tiny, incredibly organized, complex system, even exist? Well, it has to constantly fight back. It has to constantly work to maintain its order against that universal tide of chaos. And this constant battle between order and chaos, it plays out in the cell's chemical reactions. These reactions are all about something called free energy, which is just the slice of energy that's actually available to do work. So you have two kinds of reactions. Some are exergonic. They're spontaneous, they release energy. Think of a ball rolling downhill. It just happens. But then you have the really crucial ones for building things, the endergonic reactions. These guys require an input of energy. They are absolutely not spontaneous. This is like trying to push that ball uphill. So that leads us to the central puzzle, right? How does a cell pay for all these essential but totally non-spontaneous uphill projects? How does it build complex proteins or copy its own DNA when the fundamental laws of the universe are basically screaming that everything should be falling apart? Well, the answer is a brilliant piece of molecular engineering. The cell came up with a universal, rechargeable, and super easy-to-spend form of energy cash to pay for all its work. Everybody meet ATP, adenosine triphosphate. This molecule is the dollar bill of the cellular economy. It's the go-to currency. See, it carries this little packet of high energy in its chemical bonds, specifically in its phosphate groups. And whenever the cell needs to pay for one of those tough uphill endergonic reactions, it just snaps off one of those phosphates, releasing a burst of energy right where it's needed. It's incredibly efficient.
Okay, so the cell's got its cash, right? It has ATP. But you and I both know that just having money isn't enough. You need a workforce to actually do the work. And let me tell you, the cell's workforce is something else. It's highly specialized and just unbelievably fast. But there's a catch. Even a reaction that's supposed to be spontaneous, one of those downhill ones, it still needs a little push to get started.
It's an initial investment of energy, and we call it activation energy. You can think of it like the startup cost for a business. Even if the business is guaranteed to make money, you still need that initial cash to get it off the ground. And if the cell couldn't lower this cost, its reactions would be so slow, life just wouldn't be possible. And this is where enzymes come to the rescue. Enzymes are these amazing proteins that act as biological catalysts. Their one job, their entire purpose, is to grab onto the molecules in a reaction and dramatically lower that activation energy, that startup cost. They make it so much easier for reactions to happen. And are they fast? Oh yeah. Some enzymes can process millions of reactions every single second. They are the reason metabolism can happen at the speed of life.
So how do they do it? The whole process is just so elegant. First, the molecule that needs to react, we call it the substrate, it binds to a special spot on the enzyme. Now, it's not like a rigid key fitting into a lock. It's actually cooler than that. The enzyme changes its shape just a little bit to hug the substrate perfectly. This is called an induced fit. Think of it like a firm, perfect handshake. That handshake puts just the right amount of stress on the substrate's bonds, making it way easier for the reaction to happen. Then, boom, the enzyme releases the new products completely unchanged and ready for the next customer. A perfect, reusable tool.
And these master workers are total specialists. We're talking one enzyme, one job. They're not generalists. They're also completely reusable. They don't get used up in the reaction. And, like we said, they're insanely efficient. But they're also a bit sensitive. They need the temperature and the pH to be just right. This incredible specificity is exactly what gives the cell such fine-tuned control over its entire economy.
All right, let's put it all together now. We've got the currency, ATP. We've got the workforce, enzymes. How do they team up to pull off the impossible, moment by moment?
Okay, check out this graph. Imagine a cell needs to build something we'll call molecule X. If you look at the energy levels, the product, molecule X, has way more energy than the ingredients you start with. This is that classic uphill battle we talked about, an endergonic reaction. And on its own, it's just not going to happen.
So, let me ask you, based on what we've seen, can the cell just build molecule X by itself with no help? The answer, of course, is a definite no. The reaction is non-spontaneous. It's trying to push that boulder uphill against the laws of physics. But the cell has this incredibly clever accounting trick up its sleeve called energetic coupling. Here's what it does. It takes a really downhill energy-releasing reaction, the perfect example being snapping that phosphate off an ATP molecule, and it uses the energy from that reaction to pay for the uphill reaction it needs to get done. It couples them together.
So, let's go back to our problem. This time, the cell has ATP. It has the currency. So, by coupling the energy from breaking down ATP to the job of building molecule X, can it do it now? Yes. Absolutely. It now has the cash to pay the energy bill. And this graph right here shows the final, crucial piece of the puzzle. See, just having the energy from ATP isn't quite enough. The reaction would still be painfully slow because of that massive activation energy hill, that first bar. But then you add an enzyme, and look what happens. That hill, that startup cost, gets drastically lowered. That's the second bar. The enzyme makes the reaction not just possible, but fast. So you see how it works? ATP pays the bill, and the enzyme paves the road. So what's the big takeaway here? It's that cells don't break the laws of physics, not at all. They are masterful economists that have learned to exploit those laws with breathtaking efficiency. They use the universal currency of ATP and the hyper-efficient labor of enzymes to build these incredible pockets of order and complexity in a universe that's always trying to pull everything apart into chaos. And that brings us to one last really important thought. We've seen just how perfectly balanced and interconnected this whole cellular economy is. So, what happens when just one single worker, one type of enzyme, goes on strike? What happens when one tiny part of that beautiful machine breaks down? That's a story for next time.